This is AQA A-Level Chemistry. It's part 3 of the aqueous chemistry topic. As always, I'm going to recommend that you pause and have a go at the activities for yourselves as you go. So in this video, we're going to take a look at ligands, but in the context of them substituting rather than acid-base reactions. And to begin with, quick reminder of the definition. What do we mean by the term ligand? Well, a ligand is any atom, ion or molecule that will or can donate a pair of electrons, so it will form a coordinate bond specifically with a transition metal ion. Let's move on and take a look at a ligand substitution reaction. We're going to look here at the general metal M, so MH2O6 plus 2, I can add NH3, and you can see there is a straightforward swap. The NH3 kicks out the H2O. Take a look through the equations, have a think about the questions that follow, and then we're going to review. So, the overall complex charge has not changed. It's stayed plus 2 right the way through. Well, that's because NH3, just like water, does not have a charge. What's happened to the shape of the complex? Well, in each case, there are 6 ligands. That means there's no change. It's octahedral, bond angle is 90 degrees, and its coordination number is still 6. There is no change there. Now, the overall equation for that would be what? Bearing in mind we're starting here and ending here. How would you write the overall equation? Well, I know what I'm starting with, COH2O6 plus 2. If I'm going to get 6 ammonia ligands, I need 6 NH3 there. And if I've got 6 of them, I can see the complex I'm going to make. Remember, the charge stays the same. And I'm going to have 6 water ligands left over. In an exam, you might be asked to write stepwise. You might be asked to write overall. So be prepared for that either way and always read the question carefully. Let's make it a bit more complicated, though, because we already know that ammonia acts as a base. So what would happen if ammonia reacted with water? Well, ammonia reacts with H2O, NH3 and H2O to make ammonium hydroxide. That's made up of an ammonium ion and a hydroxide ion. And it's that hydroxide ion that's really important. That's why ammonia acts as a base. And this actually adds a little bit of complexity to some of the complexes and some of the complex reactions that we are going to look at. So if ammonia can act as a ligand, it will only do that if you add it in excess. If you add it in small amounts, it acts as a base. So, what would it look like? Think really carefully about this. What would the equation be if I added a small amount of ammonia? Well, my COH2O6 plus 2 would react with OH minus. And that OH minus would go on to make COH2O5 OH plus, and we'd also end up with the H2O. I've also gone on to balance this to do the overall equation. So you can see that I'm adding 2 OH minus, I'm making 2 H2O, I'm going to my solid precipitate here. And again, I'm going to talk about the observations you'll make in the final video. This is all about adding an understanding of why we see what we see. What also makes this potentially a little bit more straightforward is that we will not ever see ammonia act as a ligand if our complex has an M plus 3 ion. And there are specific examples where it will act as a plus 2, where it will act as a ligand with plus 2 ions. But again, remember, it's only going to act as a ligand when we have an excess. Otherwise, we're going to see what we have seen in this reaction. It will act as a base. Okay, so have a think about what might happen with copper. Copper undergoing ligand substitution reaction. So this, we've added an excess of ammonia. We're told that it can replace 4 of the water ligands. What would it look like? Well, we've seen a very similar one. We did it in the example earlier here with M, where the ligand substitutes the water. So I'm going to jump straight to the answers here. We're going to see the ammonia kick out of water, ammonia kick out of water, ammonia kick out of water. But the difference here from the general one that we saw earlier is that we stop when we get to Cu NH34 H2O2. Still +2, still aqueous. You are going to have to remember that that is the final complex. Simply a fact. But also you need to remember that had you been asked to add a small amount of a small amount of ammonia, we would have actually done that reaction by adding OH- because we would be looking at an acid-base reaction. Now let's complicate this a little bit more. What would the overall equation be? Well, for copper, if I added a little bit of OH-, it would be, or a little bit of ammonia, sorry, I would be doing that as OH-. It would take me to this reaction. But I could then add more ammonia, an excess of ammonia, and that would substitute 2 of the H2Os and 2 of the OHs, giving me 2 H2O and 2 OH-. If I were to just think overall beginning to end, I've added ammonia, it's in excess. I could say this, Cu H2O6 plus 2 plus 4 NH3 goes to Cu NH34 H2O2 plus 2 and 4 H2O. The reality is a little bit more complicated because I have added more ammonia. That ammonia has yielded OH- ions, which has reacted initially. So at the most complex, the most complicated, this is what we would be looking at. Cu H2O6 plus 2 is going to be reacted with 6 NH3. 4 of those NH3s are going to become ligands. 2 of the ammonia are going to become ammonium ions by accepting protons. And that's going to take it back to NH4 plus. 4 H2Os, because we've kicked out 4 of the H2O and 2 H2O gaining a proton, and we're going to get 2 ammonium hydroxide. This is a very complicated bit of chemistry. So take a look at it again. We end up, you can see that this is balanced, recognizing that the 6NH3 have been added, but that we're only replacing 4 of them, and some of them we have got an acid-base reaction. The reality is most questions are going to focus on what we see in purple. Finally, on this section, we're going to look at the complex shape. The copper will surround itself with 4 ammonia ligands. The water ligands will be on opposite sides. The overall charge here will still be +2. Water is a poorer ligand than ammonia. What do we think that will mean about its bond length? Well, the CuO bonds are longer than the CuN bonds. And that means that the octahedral shape is actually slightly distorted. These bonds are slightly longer, on opposite sides to each other. And finally, we're going to look at further ligand substitution reactions, because we can also look at chloride ligands, chloride ions acting as a ligand, and that's commonly done with HCl. This is a specific example that you will need to learn and remember. Have a read of it, have a think about the equation that will follow, see what you can do. So, we are told that chloroligands are bigger. We can only fit 4 around them. They are going to form tetrahedral complexes. Every complex we look at is octahedral, apart from those with chloroligands that are tetrahedral or that contain a silver ion, and they are linear. They are important facts to remember. When we do this, we're going to end up with CuCl4. The overall charge here is 2-, because 4 Cl- ions and a Cu plus 2 takes us to -2. All of the water ligands have been kicked out. So we get this, an equation you are going to need to replicate in the exam potentially. The ligand will look like this. It's tetrahedral in square brackets with the -2 charge on the outside. Tetrahedral, bond angle 109.5. You are also going to need to remember the colour changes here. We start with a pale blue solution. We end up with this, which is a yellow solution. But there's an added complication here. Because if I have a blue solution turning yellow, it may first appear green, as the blue and yellow colours are mixed. Going to finish off this video by looking at chelation. We looked at this in transition metal complexes, and it is just a very quick reminder. What do we mean by the term bidentate ligand? A bidentate ligand can form two coordinate bonds. It can donate two lone pairs of electrons. You might be thinking of 1,2-diaminoethane or ethane dioate ions in this circumstance. And there is an ethane dioate ion. We can have two coordinate bonds coming from the two lone pairs that I've drawn on. A multidentate ligand, well, that can form multiple coordinate bonds. It can donate multiple lone pairs. EDTA is the key example here. That can form 6 coordinate bonds. You will not need to be able to draw it. So, some equations. Have a go at writing out the equation for if the CuH2O6 plus 2 reacted with ethylene diamine. Well, actually, there's a shortcut here. You can represent ethylene diamine as En. I get 3 of those, still coordination number of 6 coordinate bonds, but 3 of the ligands. No overall change on the charge, and the 6H2O have been kicked out. What about if I take COH2O6 plus 2 and EDTA minus 4? Well, that can form 6 coordinate bonds, so that EDTA replaces all 6 water ligands. So we end up with this equation. And again, there's a link to thermodynamics here. What would happen in terms of entropy? Well, there would be a huge increase in entropy here. Why? Because we have got a large increase in number of molecules. Specifically, and sometimes they like you to use these numbers in the exam, we have 2 molecules going to 7 molecules. That is a significant increase. That takes us to the end of this video. Thank you for listening, and goodbye.